That was Galileo by Declan O'Rourke. Next up we have Galileo by some guy. Galileo is often considered the father of science. What a guy. He kind of sort of responsible for starting a revolution in a sense. Not to say that there wasn't instances of this happening before, but first guy to really make waves and start a revolution in the sense of using observation data to prove a point or to validate a theory, not just your gut feeling or you know what what you see, because sometimes what you see is not really what's going on. There's often a deeper hidden message in many of the things that happen in our universe. So we can thank Galileo for really putting his life on the line in many senses. He easily could have, if he maybe didn't know the right people, or pushed a little too hard, he might have been executed for doing what he did, as we saw in that video. But still, yeah, he rocked our scientific world, to put it shortly. He was an Italian guy, lived in Florence, Italy, also lived close to Rome, moved around a little bit. Since we watched that nice long video on Galileo, I won't go into too many details, but again, father of experimentation. Let me fix that. Bam! Done. Father of experimentation. First person to experiment with inertia and gravity. Not to say that people hadn't jumped up and down before. That's kind of experimenting with gravity. People hadn't pushed things. That's kind of experimenting with inertia. But he took data. He was like, "Hey, I'm gonna observe some stuff and not just make guesses. I'm gonna like purposefully look at this, limiting certain variables and etc. etc. Right? Pretty cool. First person to study astronomy using a telescope. What an honor, right? For basically all of history, farther than the naked eye can see, anything farther than the naked eye could see was hidden to every human in existence until Galileo decided to take that telescope and point it up at the sky. Now, he's famous, right? And he didn't invent the telescope. He made it better. It was invented by, I forget the guy's name, but for a while it was just a toy at parties to kind of amuse people. But who's to say one of them didn't look up into the sky? But their telescopes weren't as refined as Galileo's because he improved his. Plus, they might have just looked up and been like, "Oh, okay, cool. Well, let's look somewhere else, right?" But he was the first one to experiment and write down his observations and publish for so that what he saw could be passed down from generation to generation and be marked in the record books for all of eternity, or until those records hopefully never get destroyed. But who's to say? Big asteroid won't come and just bam, destroy everything. But still, what an honor! The first person to see the moons of Jupiter ever. Wow. Telescope is a very basic two-lens model with a slide adjust. That's one he used anyway. There's other types of telescopes now. And it allowed him to see things 10 times their normal size. This is a bill, a monetary unit. And this is what 10 times magnification would look like. Admit it! Can you see this? Admit it, you only invented a thing to ogle at her in number 63. I don't see her anyway. That's hideous. Next. So this is an excerpt from Galileo's published works. You got Jupiter here, and these little stars that moved around, which he eventually realized were moons. 3, meaning one of them is behind the moon. 2 of them are behind Jupiter, or maybe in front. 4, total of 4 big moons. Now we know that there's more. There's like 60 something. And this helped support heliocentricity, because no longer was everything orbiting around the Earth. Something orbited around Jupiter, Jupiter's moons. He also looked at Venus and saw that Venus had phases, which also helped support the heliocentric model because the only way that could happen is if Venus was between us and the Sun, just like the Moon is. Although the Moon's a little different because Venus is always between us and the Sun, but sometimes it's on the other side of the Sun, whereas the Moon is always on our side of the Sun. Anyway. Discovered the 4 Galilean moons, named them after those people there. Yeah. And he realized that planets are round, Earth-like. They're not just points in the sky like stars. And Venus has phases like the Moon. He discovered that the Moon was not smooth. It had craters and mountains. What? A heavenly body is not perfectly smooth and round? It's like the Earth with mountains and craters? Whoa. He discovered that the Sun had sunspots. Sunspots are moving. Of course, he eventually went blind due to this, so word to the wise, don't look at the Sun without protection. Tycho Brahe, another big guy, nice looking guy here with the jersey, Goonies, with Sloth. Sloth love Chong. Anyway, great movie. If you haven't seen it, check it out. Hired by the Denmark king, and he died at dinner via a bladder explosion. I think that's exaggerated. I think he just had a bladder infection. And back then, you had all these like proper clothes on, and didn't want to. It was rude um, to remove yourself from the situation to use the bathroom to excuse yourself, and so just held it, and that was not a good thing. So word to the wise: don't look at the Sun. Don't hold in your pee. If you do those two things, you're gonna live a long, healthy life. He hired Kepler a year before he died, which was good because Kepler was genius. Tycho was a data collector, but he didn't really have the mind to take that data and analyze it and come up with a theory. Kepler really used his mind to take all this data and come up with a theory. Here's Brahe's telescope. It wasn't a telescope of the sort that that would magnify things. It was just basically a very accurate locator in the sky, so you could use it to locate the positions of stars and planets to a very high degree of accuracy. And this allowed Kepler to come along and basically come up with the laws of motion of planetary bodies. Excuse me. So here we got Johannes Kepler. He was a German mathematician. He was a total theorist, not an observational astronomer like Tycho. He took Tycho's observations, which, by the way, good thing that Tycho died because Tycho was very selfish. He didn't want to share his observations, especially with Kepler, because I think he knew how brilliant Kepler was and didn't want to lose the spotlight to Kepler. But his theories came from his mind, not external evidence. This is very similar to other greats, such as Newton, Isaac Newton, and more recently Einstein. Einstein is completely known for this. It's harder for this to happen these days because we're at a point where you have to, theories get so complicated and you have to learn so much previous material just to get anywhere. But yeah, he was a theorist. And three of his most famous theories are the 3 laws of planetary motion. The first one is the path of each planet around the Sun is not a perfect circle, it's an ellipse. I have a little applet thingy here. So an ellipse is this. It's like an egg-shaped thing. Perfect circle has an eccentricity of 0, and as the eccentricity gets larger, we become more stretched out, more elliptical. Alright, so let's do the most exaggerated that this is capable of. And start the animation. And just observe the motion. As far away from the sun, slow. Near the sun, quick. Slow, speed up, speed up, speed up, fast for the slow, 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 slow. Slow, speed up, speed up, speed up, speed up. Alright, that's Newton. That's Kepler's first law. Second law of planetary motion, each planet revolves so that an imaginary line sweeps over equal areas and equal intervals. So this will show that. Um, so you listen to the beeps. The beeps come at equal intervals. So you got tick, 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 and each tick is the start of a new sweep. And you're gonna see the areas and how they look different, but they are equal areas. So let's just start sweeping. Right now it's 1/14 of each sweep is 1/14 of the total ellipse. All right. So I think there should be 14 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? And each of these are all equal areas. The area of this green one is equal to the area of this uh, magenta one. So they're all equal. In order for that to happen, you have to go since it's closer here to the edge. You have to have a larger arc length so that this area can be equal to that. This is just like more spread out. And so you have to move faster here in order to make a larger arc length. Move slower out here to make a shorter arc length. Alright, that's Kepler's second law. Third law, the square of the orbital period is equal to the distance to the sun cubed. That's just an equation. We don't do math in this class, so you're not going to have to calculate any of this. But just realize that this P is for period, and D is distance to the sun cubed. So this is not easy to come up with. You really need lots of accurate data to come up with this. And this is horrible. I'm going to try to fix this. Bam! Fixed. Look at that. Pretty sweet, huh? Alright, next. So the shape of an orbit is ellipse. The sun is at one of the foci. The other one usually empty space, and planet goes around in elliptical shape. Circle is perfect. Ellipse is stretched out, increasing eccentricity. Said all this before. Law of equal areas. The area of this is equal to that. This is perihelion, remember? Aphelion, we learned this in the Mars unit. And second law, basically again, in same thing, equal areas. So December, the month of December, you would cover this much distance to have this area, which is equal to July. You only cover this much distance in the orbit, but your area is the same size because it's a longer piece of the pie. And third law, again, can I do this in 20 seconds? Really? It's just, well, we'll continue with the third law in the next video. And ta-ta!